Hello, my name is Peter Oliver. I'm a graduate student at Oregon State University, and I will be presenting our work on scalable hypergraph visualization, which is a collaboration between myself and my advisors, Dr. Eugene Zhang and Dr. Yue Zhang. Hypergraph visualization is extremely valuable for exploration of large datasets because it allows us to discover patterns and structures within the data that cannot be easily observed otherwise. The problem of hypergraph visualization poses two major questions. Firstly, how to visually represent the elements of a hypergraph, and secondly, how to effectively and efficiently generate layouts within a chosen visualization metaphor. Our work focuses on this second question using what is known as the polygon visualization metaphor. I'll start by reviewing some basic concepts related to hypergraphs and polygon-based visualizations. Then I'll give an overview of how our system addresses scalability issues for layout optimization. I'll also touch on some new theory that we've developed for hypergraph planarity, and we'll wrap up by showing some results and future research directions. To begin, let us consider where we might encounter hypergraph data in different domains. Hypergraphs can emerge wherever we have polyadic relationships between sets of entities. An example of this is in the film industry, where each film can be thought of as a polyadic relationship between its cast and crew members. We can find similar relationships in academia, international trade, and just about every other field. A straightforward way to visually represent polyadic relationships is to draw each entity as a point in the plane and the relationship between them as a polygon. This starts to get more interesting when we consider networks of polyadic relationships like the one shown here. In essence, a hypergraph is a network of polyadic relationships. Using the language of hypergraphs for our film example, we call each entity or actor a vertex, and each polyadic relationship or film a hyperedge. More formally, a hypergraph is defined in terms of a set of vertices and a family of hyperedges, each of which is a subset of the vertex set. Within this hypergraph, we can begin to observe a number of combinatorial features like the degree of a vertex, which indicates how many films an actor appears in, or the cardinality of a hyperedge, which indicates how many actors are in a particular film. We also have concepts of adjacency between pairs of vertices, or pairs of hyperedges, and we can even consider larger combinatorial structures, such as walks, paths, and cycles, among the vertices and hyperedges. But I want to take a step back for a minute and revisit the visualization metaphor that we're using here. The polygon visualization metaphor is part of a larger class of visual representations known as region-based metaphors. In each of the methods shown here, hyperedges are drawn as closed regions and vertices as either points on the interior of their containing hyperedges, as in Hypervis and Euler view, or on the boundaries of the hyperedges, as in Zhaikov's method and the polygon metaphor. In Zhaikov's method, hyperedges are drawn as arbitrary closed curves that pass through each of their contained vertices. The polygon visualization metaphor further restricts this by requiring that the closed curves be near regular polygons whose vertices coincide exactly with the vertices of the hypergraph. A major advantage of this method is being able to quickly determine hyperedge cardinality by these easily recognizable shapes like triangles, squares, pentagons, and so forth. In 2022, Chu et al. Proposed a set of design principles for optimal polygon layouts summarized by these 4 points. Firstly, that all polygons should be near regular. Secondly, that the size of each polygon should be proportional to its cardinality. Thirdly, that any unnecessary overlaps between polygons should be avoided. And lastly, that any unavoidable polygon intersections should also have near regular shapes. Our example layout meets all of these criteria, so we would consider it a high-quality layout for this hypergraph. Chu et al. Also developed an automatic layout optimization framework based on these design principles, which works well for datasets with tens to hundreds of elements. However, as we increase the size of the hypergraph, finding a high-quality layout where the polygons are near regular and non-overlapping becomes quite difficult. Our new framework aims to address this scalability issue and can produce near-optimal layouts for hypergraphs with thousands of elements. We achieve this using a pair of countercurrent processes. First, a simplification phase that scales down the input hypergraph, and second, an optimization phase that refines the layout while reversing simplifications. During the simplification phase, we iteratively apply atomic simplifications to the input hypergraph, defining a hierarchy of simplified scales. We continue this until some user-specified criteria are met and the coarsest simplified scale is reached. These criteria can be based on any number of factors, such as a target number of elements in the coarsest scale, or some combinatorial property like linearity or planarity. Next, we apply an automatic layout optimization scheme to the coarsest simplified scale, which is a modified version of the optimization scheme from Chu et al. The goal of this simplification phase is to make the initial optimization of the coarsest scale more tractable compared to the input scale. Once the coarsest scale has been optimized, we iteratively invert the simplifications and locally refine the layout at each intermediate scale. We continue this until the original hypergraph scale is recovered. In this figure, the final optimized result is shown on the left, the coarsest simplified scale on the right, and one of the intermediate scales in the center. At the core of our system is a set of 4 atomic simplification operations. Our first operation is a vertex removal, where a single vertex is removed from all of its incident hyperedges and deleted from the hypergraph. Similarly, our second operation is a hyperedge removal, in which a hyperedge is detached from all of its incident vertices and deleted from the hypergraph. Our third operation is a vertex merger, where a pair of adjacent vertices are combined into a single vertex. And our fourth and final operation is a hyperedge merger, where a pair of adjacent hyperedges are combined into a single hyperedge. Using these 4 operations, our system is the first to operate on both vertices and hyperedges in a single unified framework. Here's an animation of our framework in action, where we start from an arbitrary random initial layout, first iteratively simplifying the hypergraph, and then iteratively refining the layout while the simplifications are reversed. As I mentioned before, the goal of our simplification phase is to make the layout optimization process more tractable. Much of our work on this problem has involved investigating the cases where an optimal polygon layout is either difficult to achieve or does not exist at all. This raises the question of planarity specifically within the context of the polygon visualization metaphor. Planarity for hypergraphs was first addressed by A. Zykov, who defined it in terms of the Koenig graph representation. The Koenig graph is a bipartite graph that represents both the hyperedges and vertices of a hypergraph using graph vertices. The edges of the Koenig graph indicate containment of a hypergraph vertex within a given hyperedge. Zykov theorized that a hypergraph is planar if and only if its Koenig graph is a planar graph. While this is true when the hyperedges are drawn as arbitrary closed curves, it is not true in general within the polygon metaphor, where we have this added requirement that the hyperedges are drawn as straight-edged, convex, and near-regular polygons. This has led us to develop our own definition and criteria for planarity within the polygon metaphor. If a hypergraph can be drawn in the plane without overlaps using strictly convex polygons for the hyperedges, we say that it has a convex polygon representation. Based on this definition, we have identified 4 elementary hypergraphs that lack a convex polygon representation, which is to say that no matter how we rearrange the vertices in each of these cases, we cannot simultaneously have strictly convex polygons and non-overlapping hyperedges. We refer to these cases as forbidden subhypergraphs and claim that any hypergraph containing at least one of these cannot have a convex polygon representation. We provide more information on these definitions along with a proof of this claim in our paper. Aside from the issue of planarity, there are other configurations which are challenging for automatic layout optimization. For example, certain initial layouts can lead to a non-convex optimization objective function, as is the case in this example, where we would need to either increase the amount of polygon overlaps or decrease polygon regularity to untangle this cycle structure. Another challenging case is when we have a particularly high degree vertex with not enough angular space around it for all the incident hyperedges to be drawn as regular polygons. On their own, these 2 cases are still somewhat readable, but they become much worse as we increase the scale. In this example on the right, there are far too many overlapping polygons around the central blue vertex to distinguish between them. We use our newly developed theory on hypergraph planarity to guide the selection and ordering of atomic operations during the simplification phase. Given the input hypergraph shown here, if we specifically target forbidden subhypergraphs, we get a result that looks like this, where many of the clusters of overlapping hyperedges have been removed, but we still see significant overlaps around some of the high-degree vertices and large hyperedges. If we instead target the elements surrounding these high-degree vertices and large hyperedges, we get a result that looks like this, where most of the hyperedges have been reduced to only having 2 or 3 vertices. In this view, we have lost quite a bit of information on the relative sizes of the hyperedges. If we use a measure like betweenness centrality to target elements with a low centrality score, we get a result that looks like this, where only the core elements have been preserved. In our system, we combine each of these terms into a single priority measure, which we use to rank all the possible simplifications. These first 2 terms are used to eliminate portions that are prone to polygon overlaps and thus difficult to optimize, while the third centrality term helps to ensure that we do not simplify too much of the core structure of the hypergraph. Our combined priority measure gives a result like this, where the overlaps are reduced, and we can still somewhat distinguish the cardinalities of the hyperedges based on the relative sizes of the polygons. Turning to some of our results, our framework is able to significantly reduce the number and size of polygon overlaps compared to the method of Chu et al. For hypergraphs containing thousands of elements. Where their system becomes stuck at local minima in the optimization space, ours is able to circumnavigate many of these situations through the iterative simplification and layout refinement processes. In summary, our work introduces a novel top-down and bottom-up layout optimization scheme for hypergraphs, which incorporates a multi-objective and priority-guided simplification process that is based on novel theory for hypergraph planarity. Moving forward with this research, we hope to further increase the efficiency of our layout optimization process, which remains as the main bottleneck for our framework. We also plan to explore the possibilities of using multiple simplified scales in a single coordinated visualization, possibly utilizing embeddings of hypergraphs in different spaces. Finally, we would like to thank our anonymous reviewers for their constructive feedback throughout the revision process. Thank you all for listening, and please read our paper to see all of the details of our work.